This section is functions and graphs. Most of this you have seen in college algebra. Okay, first, functions. A function is two sets, an input set and an output set, and a rule that assigns to each input exactly one output. In schools, we use the function machine model that looks like these green things at the bottom. So you input -12 and you output even. You input 0 and output even. Input 17 and output odd. Input -3 and output odd. On the next slide, we'll answer the question, what is the rule for this function machine? So here's the machine again. Complete the input-output table by using this function machine rule to fill in the output row. So when we input -7, what would you expect to get out? Well, if I look at -3, I would think that this would probably come out to be odd. -1, again, I would think the answer would be odd. If I input 6, though, that looks like it's going to be an even, and 102 should be even. Now we're going to create a function rule. So my rule says that numbers divisible by 2 are even, numbers not divisible by 2 are odd. Functions can be described in words like my favorite color, so everyone in the class could say their one favorite color. That would be a function. In symbols, y equals x minus 7 is a linear function, or an arrow diagram. You'll see it on the next slide. The level where we see functions in school is going to be 8th grade or pre-algebra if you have pre-algebra students in 7th grade, and mostly in algebra, algebra 2. It's important to realize that most things we talk about in algebra and math are functions. Okay, here's that arrow diagram that was mentioned. So describe a rule for assigning each element of the input set to an element of the output set. So 46 goes to 23, 18 goes to 9, 120 goes to 6, 7 goes to 3.5, 25 goes to 12.5. So it looks like each input is assigned to half its value in the output set. Okay, another example. This time you have an ordered pair. 10, 7 goes to 17. Notice also that 15, 2 goes to 17. This is still a function because 10, 7 only goes one place, even though 17, an output can have 2 arrows, but an input can only have 1. So the rule here is that we're assigning each input to the sum in the output. Here's one using geometric shapes. So each geometric shape is mapped to its area or number of blocks. For example, if you count just the rectangle, it has 4 and it's mapped to 4. This one maps state names on the input to their capital on the output. That's a function because each state only has one capital. Elements in a function may be different types of objects, numbers, geometric figures, words, etc. Usually in math, they're numbers and variables. 2 or more elements in an input can map to the same in an output. The requirement is that each element in the input set cannot be assigned to more than one output. So ask yourself, can the first element be assigned to more than one second element? If so, it is not a function. Okay, so let's look at these two statements, number 1 and 2, and decide if they represent functions. So number 1 says each person is assigned to his or her social security number. So for each person, how many social security numbers can they get? Just 1. It should be 1. We'll just assume it's 1. For number 2, each amount of money is assigned to the object it will buy. That is not a function. Okay, so if we think about it, $5. If you go into Walmart with $5, can you buy only one thing? No, you could buy, there's lots of things that you could get for $5. Think about taking $1.25 into the Dollar Tree. You can buy almost everything in the store for $1.25 each. So that is not a function. The rule for a function is often defined by an algebraic formula. An arbitrary element of the input set is a variable such as x. So x is the unknown. The corresponding element of the output is f of x. Okay, you saw that in college algebra, f of x. That means the function in terms of x. It does not mean f multiplied by x. For an input element x, that f of x also represents y. So these two are interchangeable. We use f of x because sometimes that notation is simpler in higher math. Okay, you have the input set and the output set. Consider the rule 3x plus 1. We would write that as f of x equals 3x plus 1. Then, if I wanted to know, well, what happens when x is 5? I would write f of 5 equals 3 times 5 plus 1 is 16. F of 0, and I would substitute 0 where x is, and get 1. Okay, this time we're going to write algebraic rules for each of these functions, and the input will be all the whole numbers, and the output, x is the input element. So f of x, where each element is 3 more than twice its value. 3 more than twice its value. And you can see the answer there. For g of x, we have 1 more than 4 times its value. 1 more than 4 times its value. And you could have put 3 plus 2x. You can switch the order on those two because addition is commutative. On number 3, we're going to evaluate f of 45. So we're going to put 45 times 2 plus 3 is 93. And 56. So 56 times 4 plus 1 is 225. I'm going a little bit faster here because hopefully you kind of remember some of this from college algebra. Okay, we spend a lot of time in math talking about linear functions, so those make straight line graphs. Let's say we cost $8 to rent a lawnmower. It will cost you $16 for 2 hours, $24 for 3, $80 for 10, so it's the same rate the whole time per hour. If x denotes the number of hours and f of x the total cost, then renting a lawnmower can be written as f of x equals 8x. Now, if there is an initial fee of $5, in addition to that, the equation becomes 8x plus 5. In general, the constant rate is the slope of a line. Okay, I highlighted all those. The constant rate was $8 an hour. It's the number in front of x. That is the slope. And the initial cost, $5, is the y-intercept. Okay, now tie this to what you did in college algebra or in Algebra 2, Algebra 1 in high school. We used the formula y equals mx plus b. I like to think of that or teach that as m, which means is the Latin for slope, means move. That's how we're moving or changing, so $8 an hour. And b is where we begin. We begin at $5. Here we have a word problem about a copy center. If we send a fax in state, it's $4 for the first page and $1 for each additional page. If we send it out of state, it's $5 for the first page and $1 for each additional page. The first question is, what are reasonable input values? So what kinds of numbers could we use for the number of pages? We wouldn't use negative numbers, decimals, or fractions, and you probably wouldn't send 0 pages. So how about 1, 2, 3, 4? If those are our input numbers, what are our output numbers? So if I send 1 page in state, it will be $4, then the next one will be 5, then 6, 7, 8, 9. If I send out of state, it's going to start at 5 because the first charge is $5 and then $1 more each time. This graph shows the costs. Find the points on the graph that show the cost for 8 pages. What are the corresponding points and what is each cost? So if we just go to 8 on the axis and go up, you'll see that the in-state is $11 and the out-of-state is $12. If x represents the number of pages, write expressions f of x and g of x for the in-state and out-of-state. So x plus 3 for the first one and x plus 4 for the second one. And you see that works for 8 plus 3 is 11 and 8 plus 4 is 12. Okay, here's a different example showing the revenue from a middle school dance. After the first 100 tickets, the price increased, and you can see that because about halfway through the graph, the line gets a little steeper. So the first question is, what was the revenue and cost per ticket for the first 100 tickets? So I highlighted those. I went up from 100 numbered tickets and across, and it cost $200 for 100 tickets. So that means that each ticket was $2. This time we want to know the cost of the second 100 tickets, the ones that cost more. So first I highlighted the 200 tickets cost $500, but we need to take out the first 100 that cost $200. So you can see that here. That leaves me $300. That means 100 tickets at $300 is $3 per ticket. Now it says what is the revenue for the sales of 50 tickets. So if I go to 50 on my graph and across, I get 100. And if I go to, that means when they sell 50 tickets, they made $100. If I go to 150 on the graph and across, it comes out to 350, meaning when they sell 150 tickets, they make $350. And now we have a different graph. This graph shows the distance in meters as a function of time over a 15-second period for an inline skater's trip through the park. When is the skater going the slowest, the fastest, and not moving? So remember that time is along the x-axis and distance along the y. I like to do the not moving part first. So if he's not moving, his distance won't change. And that's the part between 8 to 11 seconds. When the person is going the fastest, the line will be the steepest. So that's the green part. And when the skater is going the slowest, that will be the more shallow line, or the purple line. This is the same graph. How far did the skater travel during the first 8 seconds when he was going slower? How fast was she going? So in 8 seconds, she went 80 meters. 80 divided by 8 is 10 meters per second. How far did the skater travel from 8 seconds to 11 seconds, and how fast was she going? Well, she didn't go anywhere, and she wasn't going any speed for those 3 seconds. Okay, now for the last part, from 11 to 15 seconds, the skater went from 80 meters to 160 meters, which is a distance of 80 meters, divided by those 4 seconds is 20 meters per second. Now it wants you to write an equation for each of those 3 parts. So in algebra, we would do this as a piecewise function. We're not getting that. You don't need to write it that technically now. We just want to think about from 0 to 8, the rate was 10 meters per second, so it's 10x. From 8 to 11, there is no x variable because it's a constant. The skater stayed at 80. And from 11 to 15, the rate changed from 10 to 20, so it's 20x. Now you're ready to start the homework on functions. You need to be able to define functions and then Gather information about rates and slopes and speeds from graphs. Good luck.